All right. So thanks for joining us again for discussion of the HeatSmart Capital Region Clean Heating and Cooling Program. My name is Wendy Mahoney. I'm the Executive Director of Sustainable Saratoga, and I'll be moderating the webinar this evening. We have two folks who are going to be giving the presentation. You've heard them chit-chatting a little bit as we're waiting for folks to come in. Todd Fabozzi is the Director of Sustainability at the Capital District Regional Planning Commission, and John, how do you say
Ciovacco.
Ciovacco, right?
Ciovacco.
Is the president of Aztech Geothermal. So they're going to be presenting tonight. I've muted everybody for now, and so we'll keep you muted throughout the presentation. I'm recording it. We'll put this up on our website in the near future. And at the end of the presentation, Todd and John will answer your questions. There's a chat box at the bottom of the Zoom that you can ask questions throughout the presentation. And I will make sure to follow up with them at the end of the presentation. You can also raise your hand at the end if you want to have more of a discussion with them, and that's absolutely fine as well. I think a lot of people are familiar with Sustainable Saratoga, but just real quickly, we're a nonprofit organization that focuses on the protection of natural resources and promoting sustainability for the benefit of current and future generations. Some of you might be familiar with some of our popular service events like Saratoga Recycles Day and Tree Toga and Repair Cafe, and then some of our advocacy work promoting sustainable policies with our government officials. We work on things, a varied array of topics from land use and natural resource protection, protecting, expanding our urban forest, addressing the climate crisis, and reducing how much we consume and waste in our daily lives. So there's no shortage of topics and work to be done in the sustainability front. And so providing educational forums like tonight is really part of our effort to make a tangible difference in the community. So thank you again for joining us, and I will turn it right over to Todd.
Thank you, Wendy, and thanks to Sustainable Saratoga for hosting this event. So the reason for our presentation is to promote heat pumps. And so as my role as the Director of Sustainability for the Capital District Regional Planning Commission, we've been getting involved with a variety of different sustainability programs, primarily through funding that NYSERDA provides. So we've been involved for quite a while in the Clean Energy Communities program, in which we help communities become energy efficient and sustainable and help them secure grant funding for clean energy projects. And about a year ago, we got involved with the Clean Heating and Cooling Program and received a grant from NYSERDA to run a HeatSmart campaign. And so that's what we call it, is HeatSmart Capital Region. And the primary purpose of the program is to promote heat pump technology, to educate people about heat pump technology, and to try to inspire the adoption of heat pump technology for people to install this technology in their homes and in their businesses. So the campaign funding is for 3 years. So we just went through our first year of the program. And of course, like everything, it got a little screwed up about halfway through it. And so one of the things that we were doing a lot of is going to different events and talking about this and tabling and presenting. And with COVID, of course, we have to transition. And so we're doing a lot of online or all online presentations for now. And so the campaign itself, the gist of the campaign, like I said, is to educate on heat pumps and to try to get people to convert their systems, if they're using, and most likely are using, fossil fuel systems, to heat pump technology because of the efficiency and the large reduction in greenhouse gas emissions for using heat pumps. So in order to do the campaign and follow the structure of a campaign per the funding from NYSERDA, what we did was put out an RFP and solicited responses from installers, and then vet those installers through an interview process to be able to get a team of installers that we would help promote. So not only would we promote the technology, but we would promote the installers. So John, go to the next slide. I just want to point out the campaign covers an 8-county area. So in order to do the program, we had to target an area. We decided to cover the whole REDC, the Regional Economic Development Council region. And so we've got a large area to cover, an 8-county area, which is a challenge. Other campaigns will often focus just on one town or one city or maybe one county. For us to cover this large of an area is a challenge. So one of the approaches that we're going to have in promoting this technology going forward over the course of the next 2 years is to create a synergy between our HeatSmart campaign and the Clean Energy Community Program, in which we cover this same area. And we have a team of outreach coordinators who work with the local governments on a variety of initiatives, and campaigns is one of the initiatives we work on. So we hope to create a series of micro campaigns throughout this 8-county area, partnering with groups like Sustainable Saratoga and municipal governments who are interested in trying to help us to promote and further saturate a smaller area, a city or a town or a village, or perhaps it's a whole county, but more targeted than what we can possibly do with an 8-county area. So that's going to be our goal, is to work on those micro campaigns going forward. So next slide, John. So as I started to say about the idea of the campaign and what we want to do besides educate, in our website that we've set up, which is called HeatSmartCapitalRegion.com, and this is on the slides, and these will be made available to you, is really the portal for not only getting some information, background on heat pump technology, but also to be able to sign up to get an evaluation from our installer team. And you would choose which installers you would want to be evaluated based on the technology you're interested in. So we're covering essentially 3 different heat pump technologies. We're doing air source heat pumps, ground source heat pumps, and hot water heat pumps. And so that's the technology we're promoting, along with energy efficiency, just basic home insulation and energy efficiency. And so this is the place where you would go to be able to get background, to be able to enroll. So we have an online portal, and I wasn't going to go through the whole website here. This is something you should do on your own, and you'll be able to see. It's very intuitive, where you can put in your information to get a free evaluation by any of our installer team on whatever technology you might be interested in. And there's also information here about the incentives and other background. So our installer team, as I started to say earlier, and so next slide, John, we put out an RFP. We interviewed installers, and they needed to be NYSERDA registered installers, but that wasn't the only criteria. Then the criteria would essentially be, a lot of it was around their enthusiasm for heat pump technology, their experience and background in the heat pump technology. And so we also had to look at how we can get coverage for that whole 8-county area, which is a challenge. So you can see these are the companies that are part of our campaign. We have True Building Performance and Global Dwelling, which are energy efficiency companies. So you can get a free home energy. It's not quite a full audit, but it's an evaluation, and the NYSERDA pays for that now. So anyone can get a free evaluation right now, and you can contact either of these 2 companies to do that. And then they also could do any of the work that was necessary if you wanted to further make your home energy efficient, insulate your home, etc. And then we have Superior Co-op. We have Hot Water Solutions. We have Ridgeline Heating and Cooling. We have Choice Heating and Cooling, and we have Aztech Geothermal. So just in the last 2, Choice and Aztech are the 2 that do geothermal. Choice actually does all of the above. They're a full service, and so they do traditional HVAC, and they also do air source, but they do geothermal. And then Aztech, and John is going to talk in detail, and he can tell you more about Aztech, but they're primarily geothermal company, though they do air source as well. And then Superior, Hot Water Solutions, and Ridgeline, those 3 just do air source heat pumps. And so again, the whole idea here is to be able to try to promote the technology, promote these companies, grow the market, And so there's not really any risk if you want to connect with any of these companies, especially if you are on a system that is, say, heating oil or propane, where the value proposition is really great for you to transition to this technology. And John's going to talk in detail about those kinds of things. But I also wanted to just point out one last thing about our campaign. Not only is it going to go for 3 years, but we are going to be opening up another RFP process near the end of this year. We started with these contractors in November, so we're looking at shooting for around that time again, in which we will open it up to see if there's other companies that want to be a part of the campaign as well, and to reconfirm with the companies that are on it that they want to continue to be on it. And for any of you that want to get an evaluation, you may decide at the end of the day, other contractors that you want to check out. From our point of view, obviously we want to promote the installers that are part of this campaign, because we know that they're good companies to work with and knowledgeable about this technology. But also, we're just interested in expanding the use of heat pumps. So it's fine if you learn about this and you go somewhere else. Well, fine, because as long as we try to transition to what's called beneficial electrification, and instead of burning fossil fuels to heat and cool your home, that you're using electricity to do that. And particularly if you can use electricity that's coming from a renewable source, if you can parlay this with say solar technology in your home, then you can really get closer to net zero, especially with a well-insulated home. So I want to just encourage you to look at our website and follow up with any questions if you have them at the end of this webinar, but also going forward, if you want to contact me directly, my contact information is on the slide that follows. And so then I'll turn it over now to John Ciovacco, who's the president of Aztech Geothermal. These guys are a great company and really know this technology. And so John can get into the weeds in a way that me, as my background in urban planning, can't. But so I'll turn it over to John.
All right. So can folks hear me? Have I successfully unmuted myself? I don't know that I have. I have. Good. I'm up and running. So I'm John Ciovacco. I'm the president of Aztech Geothermal, and I'm a mechanical engineer. I went to Union College down the street, I guess you would say. And I'm a board member of NYGEO, which is the New York Geothermal Energy Organization. We put on a big conference every year that I do the educational program planning for, which is a lot of work, but very rewarding too. I'm also just recently appointed to the Department of Public Service Strategic Advisory Group for building electrification. So I'm going to be one of 13 people statewide that's helping advise the Public Service Commission on energy policies. So that's exciting stuff that I'm just starting to get involved in too. My company, we started back in 2008 when you could be a company called Aztech Geothermal. That was kind of a combination of concern for the environment. Tax credits showed up, so we got some additional incentives, and oil prices were super high in 2008, and that was kind of the catalyst, and those combination of things that brought us into the market. So since that time, we've installed about 450 systems in the area. We do a little bit of work in Western Massachusetts as well, but we'd like to stay within a range that we can do 24/7, 365 service, so that if we install it, we service it, and we're there for you. We do a lot of work just with ground loop installation and design for folks that don't do the ground loop part of it. So we work with other mechanical contractors, and maybe we'll work with Todd's son someday. And then we do install ground source, air source, and heat pump hot water heaters. So we do kind of all the elements of the campaign, which is one of the reasons Todd's asked me to do this. We consult with engineering firms. We have a crew of guys that are terrific, and we're a HeatSmart contractor, but you knew that. If you're in the Saratoga area, you might have seen this. So this is our one of the signs that we had up. Ever controversial, but really fun for me. Serious stuff. New York State has very, very aggressive goals in terms of our energy and climate. And this is a timeline, a little hard to see if you're on a small screen, but essentially there's milestones between now and 2050. 2050 is an 85% reduction in greenhouse gas emissions based on 1990 levels. And the CLCPA, which is the Climate Leadership and Community Protection Act, sometimes just called the Climate Law, helped to really codify these things actually into law, which they'd always been kind of, these types of things had been talked about quite a lot. I'm not going to go through a lot of detail on this slide. This will be something that folks can look at after, but I did want to point out that heat pumps really focus in a few different areas. Energy efficiency is the reduction in site energy of a building. So when they have the 185 trillion BTUs of energy savings, you could do that with air sealing and insulating, but a heat pump also reduces the site energy necessary, because you don't need to deliver as much energy to a site that's getting on-site renewable energy, either from the air and for an air source heat pump, or from the ground if it's a ground source heat pump. And in fact, air source and ground source heat pumps are the largest way to reduce site energy, the amount of energy that goes. It's a different type of energy. If we've been using fossil fuels, we sort of have a sense of what is a therm, what is a gallon of oil or propane, but now we're delivering electricity, but that electricity is not actually doing the direct heating, it's really leveraging the renewable energy. And that ends up being a significant reduction. So greenhouse gas reductions is the second box here. That's obviously a big element. If we take out fossil fuels, and the upstate New York grid right now is quite clean, and as we go towards more and more renewable electricity, that'll get better. And then obviously the greenhouse gas reduction goal in the long term is a big heat pump area as well. One of the things that is a concept called latent decarbonization. And as we go to 100% clean electricity, a heat pump now that's using grid electricity that has some contribution from fossil fuels, let's say a natural gas generated electricity, if we go to 100% clean electricity, your heat pump gets even cleaner over time. So switching to electric based heating and cooling technologies and hot water and also transportation is a big deal, but that's not today's topic. But as we do that, the fact that we have a clean grid upstate is great, and it'll get cleaner as we go. So the heat pump technologies that we want to talk about are largely ground source and air source, are kind of the two big categories we talk about. Water source heat pumps really is oftentimes a ground source heat pump, is really a water source heat pump that happens to be connected to the ground, but that same technology could be used in different configurations to either extract energy from a source or deposit energy to a sink. The ground just happens to be one that's convenient to use. Heat pumps really move energy rather than generate it. They do consume electricity in doing that, but they're really using that electricity to leverage existing sources and sinks, rather than where we have something like natural gas or propane or oil, where it's consumed in the process. We deliver it, we create new energy, and that energy does what it does, and it's over. A heat pump is really trying to take advantage of existing energy that's in the environment that it can access, and then it changes its characteristics somewhat. I mean, largely what the heat pump systems we're going to talk about tonight do is they have a compressor in them, and that compressor makes refrigerant hot. That's really all it does. And then we have to figure out, okay, now that we've taken this low temperature energy, we've made it hotter with this compression cycle, just like your kitchen refrigerator, the air conditioner in your car, the air conditioner at your house now, all the same technology. It's just we're using it in ways that we're reversing that cycle so we can take advantage of its both heating and cooling capabilities, but it's not new technology. Some of the different versions of that we're going to talk about are centrally ducted systems for air source. So a centrally ducted air source heat pump really looks a lot like an air conditioner. There's many of them that just have that round style outdoor condenser. The difference is they'll reverse so that they'll be able to actually heat your house instead of just be your air conditioner. But it's really the same basic technology with the ability for the refrigerant to reverse seasonally. A lot of folks, either you might have this technology or you might know somebody that does. You've seen them. They're called ductless mini splits or mini splits, where you've got an outdoor system that's it's a compressor unit that's outside. It can be a condenser or an evaporator. It's the condenser in the summertime, kind of traditional air conditioning. It switches and becomes the evaporator. It becomes the cold side to absorb energy from the air. But these are certainly very versatile ways to electrify certain parts of your house, and they have larger systems where you could do your whole house in a ductless formation. Air source heat pump water heaters, they really are a standard water heater in terms of size. Say it could be 50 gallons. You typically get a little bit larger one. So if you had a 50-gallon electric, a 65-gallon is more the equivalent in an air source heat pump water heater in terms of performance. So you might need a little bit larger capacity. But on top of that unit, it has really the same basic refrigeration system that you might get in a dehumidifier that you might find in someone's basement. It's a small compressor, and it's basically taking thermal energy from the basement or whatever the air is around it, and it's taking the warmth out of it, compressing that, making it warmer, heating the water with it, and then you actually get a little bit of cooling and dehumidification in the area that it's at. It's not a dedicated dehumidifier, but if you have a damp basement, it can at least be helpful and can actually make your dehumidifier won't run quite as hard. So there's a little net savings in that too. There are also air source heat pump systems, sometimes called VRF, variable refrigerant flow, that we tend to see in much larger applications where those outdoor units would be quite large. Then maybe this unit here might be a 3 or 4 ton unit, 1 ton unit even, the mini split. These might be 25 tons each, so that might be 100 tons of capacity. And then they would serve a whole number of different units inside the building for different zones. These systems have the unique capability of being able to share energy. If I'm using this unit in a conference room that's loaded with people in a training and it's in air conditioning mode, this unit might be in heating mode to heat an office in the wintertime, but they can share energy without involving the compressor to actually save even more energy. So those are kind of neat systems. Those also can be ground source or water source connected instead of having that air source condenser outside. Geothermal systems come in a few different varieties. A lot of times we talk about how we connect to the ground. The most common is a vertical system where we drill straight down, much like you install the same equipment that we use for water well drilling largely, and then we stick a tube down there and we circulate it's a closed loop system where the water that we're using as a heat transfer fluid, we're not actually using the water from the well very often. You can do that. There are open systems that you see down in this corner where we might pull from a water well, use that energy, and then put it back into its separate well or put it back in the same well. Those are becoming less and less common. Those were quite common years ago, but due to some of the maintenance issues and contamination that you can introduce to the system, they've kind of fallen out of favor, I would say, but I'm happy to talk to people about that if you're interested. Horizontal systems, we only go about 6 feet down in this area and bury pipes to get thermal energy out of the ground. That can either be a straight system or a slinky system. My company has maybe 14 pond systems, and that's a dedicated pond, usually on someone's property that they own and control. I'd like to see if I can get a 1/4 acre, 1/2 acre, or more. So it needs to be a pretty sizable pond, but that can be a nice exchange mechanism as well without a lot of excavation if the pond is near the house. There's also this concept of direct exchange where the refrigerant system that is moving the refrigerant and compressing and has this hot and the cold side, the condenser and the evaporator, they actually put the refrigerant right into the ground. So these are copper pipes that are in the ground, and the refrigerant that's in the heat pump is actually being cycled to the outside, and that is either the condenser or the evaporator, depending on how it's set up. Also, not that popular because you're putting high pressure refrigerant into the ground with copper lines that are buried just doesn't have the longevity of the polyethylene systems that we use now, which are really similar to the kind of water piping that you might have. It's not a new technology. This is from Life magazine from 1948, and a lot of very similar elements to certainly what we do today. This is a horizontal loop field that these guys are installing right here, and they're showing a diagram here of the same basic refrigeration cycle that we use now. This particular thing, I've seen this, is enormous. It would take up a good portion of your entire mechanical room and maybe a good portion of your basement. So we certainly have made them smaller since that time, but it's a technology that's been around really since the beginning of refrigeration. We've used heat pumps. They just haven't really hit the big time yet, but it looks like that's where we're headed. I'm going to talk a little bit about how ground source systems work, then I'm going to talk a little bit about air source systems. Ground source system is really taking energy that's stored in the ground. A lot of the energy from the sun is absorbed by the ground, and that's why we have very constant temperatures. And that constant temperature tends to be about the average. The ground temperature that we access is about the average air temperature of your location annually. So around here, it's usually around 52 degrees in the Saratoga area is the starting sort of the mean ground temperature once we get significantly below the frost line, usually about 20 or 30 feet down, it becomes quite constant. If we're in Miami, Florida, it's 77, because that's more the average temperature that the ground sees. So if you were in Howe's Cave, which is about 52 degrees up in our area, if there was a Howe's Cave equivalent in Miami, it would be about 77 in there. It would be considerably less pleasant. But it is a relatively constant temperature. And so that gives us the ability to take that relatively constant temperature and run it over, usually we're pumping water or water with a little bit of antifreeze out to get that energy. When we bring it in, it runs over a heat exchanger inside the heat pump, which causes the refrigerant to evaporate in the evaporator. So now the energy's been transferred to the refrigerant magically. So the water comes in, say at 52 degrees, it might leave at something like 45 degrees. So it got colder. Where did it put its energy? It put its energy into the refrigerant. It's not something that you're likely, if you're not familiar with this, understand fully, but just understand that we're transferred the energy from the ground to the refrigerant. The refrigerant now is 50 degrees really isn't a temperature we want to heat our house with. So how do we make that warmer? The gas in here, that's the evaporation, is now a gas. The compressor makes it hot. On the other side of the compressor, it's common that we'll see temperatures like 160 degrees. Now 160 degrees is kind of interesting. Now we can blow air over that, or certain types of systems will take water in exchange over it. And now we have something to warm the house with. But a lot of that energy, and this is sort of how the energy equation goes, maybe in a ground source system, we tend to get 3 parts of the energy from the ground for every unit of electricity. So we have a coefficient of performance of 4. So when we get this output of energy here, which is Q3. So right now, if I have 3 units of renewable thermal energy from the air, the ground, the lake, or a pond, and then I have this 1 unit of electricity. So that's the electricity I'm using on a motor in the compressor. That's really where most of your electricity is coming from. It's really we're pumping energy. We're not really pumping. The pumping of the water out in the loop field, that tends to be much less than 10% of the overall electricity used. So 90% of it is used by the compressor. The compressor is really the load, and it's compressing that gas as it goes. So that compressor energy is the energy that we purchase, but most of the energy comes from a renewable source. If this is an air source system, this might be 1 unit of energy from the air and 1 unit from electricity. We get 2. So what does that mean? That means it's twice as efficient as electric baseboard. And in certain operating conditions, when it's warmer out, the air source units will also have higher COPs. They'll have COPs in the 2.5, 3 kind of range for a lot of the winter. So that means they're 3 times more efficient than electric baseboard. So we're using electricity to leverage energy that we can access from the air or the ground. And that's really the sort of the heat pump magic. And that's expressed in coefficient of performance for heating. And Wendy, if there's any questions coming in that you think are appropriate, I'm happy to take a pause. So what I just showed you is kind of the diagram, a schematic of sorts of a refrigeration cycle and how that relates to the efficiencies that we get. And again, don't expect people to be expert at that at this stage. This is a little bit what it looks like in real life. So the ground loop would be out here. The water would come in. There'd be a circulator on here. It would exchange thermal energy here with the refrigerant system, which then would go to the compressor, which then would go to another refrigerant coil here that we blow air over. So the air is coming from the return and blowing into here. So this is, in the wintertime, the warm coil. This is the cold coil. So this is the equivalent of what would be outside, is this coil that's inside the cabinet on a geothermal system. That would be the outdoor unit. The outdoor unit would essentially be these two components together with a fan that's blowing air over a coil. So when we use heat pumps, we don't make heat at the temperatures that we do with combustion systems. Combustion systems, if we have a boiler, it can boil if it needs to. Most boilers don't. If they're a hot water system, they're usually somewhere between 160 and 180 would be common temperatures that a boiler would go to baseboard with, or to a radiator. But a heat pump, when it makes hot water, generally, once it gets around 120, that's about as far as we want to go, or else we really lose a lot of efficiency. And then most heat pumps that we have readily available to us don't get above about 135 or 140. So they're really not boilers. So how do we deal with that if we have a heat pump system? If we have baseboard water systems, sometimes there's enough baseboard in someone's house that lower temperature will work well, but that's uncommon. More common would be we would need to put in baseboard that has much more surface area. This is a double fin. So this has much more surface area, much more fin area for the lower temperature water to get the energy into the room. Or there are certain types of radiant panels, sometimes called European radiators, that have much, much more surface area, and so they can handle these lower temperatures. Even a boiler, a condensing boiler that's set up to do that, would run more efficiently in these as well. So it's technology that's used both in combustion and in heat pumps. Radiant floors are common for heat pumps because that lower temperature heat can be distributed over a large surface area. Ductless systems, that's certainly a way. If we can only get that coil to about 120 or 130, we blow air over it, we can heat that room. We can also send water to things that look like this with certain heat pump setups. So there's lots of versatility in the types of ways that we can do this. A very common way to do it is if you have central ductwork, because central ductwork, we can size the coil inside the air handler to operate effectively at low temperatures again. Existing ductwork oftentimes needs some sizing adjustment, or we need a little more return or a little more supply. There's often adjustments we need to make. If it's ductwork in a new house, we can have it sized appropriately for that. Airflow in a heat pump tends to be more air than a combustion system would need. If I have the delivery temperatures in a combustion system right at the register, they're commonly in the 120 to 140 degrees that enters the room, and that's a room we're trying to keep at 70. So it's hot air, and that hot air will fly because it's much more buoyant, much more spread out. It'll really find its way to a higher point, and you'll have a big difference in heating and cooling from the floor to the ceiling. A heat pump doesn't deliver things like that. At the register, we're often at 90 degrees. We might be 85 degrees. And 85 degrees or 90 degrees can get a room to 70. It just needs a larger volume of air, and the run times tend to be longer. In very old leaky houses, that's tough because that house was dependent on that super hot oil system to keep it comfortable. because the air keeps washing through it as it leaks on cold, dry nights. It's hard to keep a house comfortable with a heat pump system if we haven't done some air sealing or insulating or put in a very, very large heat pump. And we can do it. We have done it. But what you would really want to do is try to air seal and insulate that building so that the heat pump temperatures can work effectively and that you lower your overall energy cost. And that's one of the reasons the HeatSmart campaign has those energy efficiency companies that are as a part of the team. So we talked about this some, but very, very common and popular. The most common is one outdoor unit. Could be the condenser, also could be the evaporator if it's the wintertime, but it's the compressor unit is outside. And then the inside, we're blowing air over to either cool or to heat. In this case, it's in a cooling mode. So that's the outdoor condenser. And this is the evaporator inside, and we're using it to cool the air down. These reverse, and when they reverse, the outside unit is absorbing energy from the outside air, compressing it to make it warmer, and then delivering it inside the house. And so this technology has really come a long way. The inverter driven is really just another expression for variable speed compressors, so they can turn up and turn down over a large range, keeps them in a very efficient state most of the time. And then they can operate down to very low temperatures. Their COPs, their efficiencies drop quite a lot at these very low temperatures, but they can continue to operate. Older air source heat pumps used to shut off around the freezing temperature, and then you would rely on a secondary heating source or backup heating source, which could be a combustion heating source, or a lot of people had electric strip heating or something like that. So trying to heat your house with a toaster, which is a COP of 1. And I think we all understand that that is not a cost-effective thing to do for most of us. Here's another kind of more sophisticated drawing of how these systems are set up. So the outdoor condenser or the outdoor unit, which is the compressor unit, is out here. The line set is the refrigerant lines, and they come up to this unit here. And then there's lots of different unit styles where you can hide that better. These tend to work the best, honestly, though. The ones that stick out of the wall have the most features or the most operable. And a lot of people find that they don't, their eye isn't drawn to it after it's there for a little while. When you first get it and everyone's staring at it, it seems like what's called a wall wart. The wall wart seems to disappear visually for most people after they've had it for a bit. Here's kind of to put everything on a scale of electric heat options, because if we're going to electrify, if we're going to take fossil fuels out of buildings for heating hot water, we can use electric resistance. So an electric hot water heater would be an electric resistance. Baseboard electric, which tend to have a thermostat in every room or right on the unit. This is a big electric boiler, actually. This is an electric fan coil. So these have what are called a COP of 1. So for every unit of electricity, I get a certain amount of heat. For every kilowatt hour, I get 3,412 BTUs reliably. I'm not leveraging, I'm just using that electricity to make heat. That's pretty expensive. If I use an air source heat pump, I'm starting to use that electricity to leverage thermal energy from the air. And so if I'm in heating mode, I might be 1.5 to 2.5 times more efficient than just an electric source, which is pretty good. And that starts to get me in the range of what heating oil and propane heating would cost for hot water and for heating. When propane and oil prices are high, the air source heat pumps tend to show some pretty good savings. When oil and propane prices are low, it tends to level out. But you're kind of in that range. An air source heat pump is generally, we can say, tends to produce a savings in an oil house right now, and propane when propane is kind of on the upswing. Ground source heat pumps and different configurations of water source heat pumps, you tend to get into the COPs of 3 or 5. So for every kilowatt hour that I have, I get 3 times more heat energy than I would say with electric resistance, or 5 times more for the most efficient systems. And that starts to approach what it costs to heat with natural gas. And when I say it approaches it, is because in our region, natural gas is very inexpensive. And so you need to be in a COP of 5. You need to have pretty much the top of the line systems, the most advanced, to get to a cost neutral kind of place against natural gas. As a result, ground source heat pumps tend to do well in the propane and oil areas because they show a very significant savings. I think we have 7 systems in downtown Saratoga, all have access to natural gas or could have had access. And those folks did it for a number of different reasons. They didn't want an outdoor condenser that was next to their pool, or they have strong feelings about the environment. And so the fact that it's cost neutral was good enough, even though it costs more to install. So everybody sort of has their choices that they're making as to why they would do these things. And over time, we're working hard to try to get the volumes of these things up and the prices down. I often get asked, how much PV solar do I need? This just gives you kind of a relative sense. So if I have 1,000 gallons of oil that I'm using to heat a house, and I have my assumptions down in this little corner down here, and I wanted to just say, I'm going to get enough electric baseboard. I'm just going to get so much solar that I'm just going to put electric baseboard everywhere, and I'm going to heat that way. Well, for 1,000 gallons, I would need, in my example that I have here with 300 watt panels, I have about 101 panels, and that's, I don't have 101 shown, but the sizes are relative in these different scenarios. If I go to an air source heat pump, I need a lot less solar. I need less than half of that. And then if I go to a ground source system, I need a lot less than that. And in some ways, from a residential standpoint, people are interested in this. But if we think more broadly, if we think we need to electrify all buildings by 2050, and a big ramp up between now and then, we also need a lot more renewable electricity to serve those systems. As we use more efficient heat pump systems, we don't need to create as much offshore wind or as much onshore wind or as much community solar. Not that those are good things, but we don't want, we're certainly want to minimize the additional expense of creating those assets if we can. So we need less clean electricity as our efficiency increases. People are interested in this, and I have my assumptions here, and it's an ever-changing thing. I don't update it all the time, but if I look at how much does it cost to heat with some different technologies, if I've got electric resistance, that's not so great. That's the most expensive. Propane and oil kind of vie for that, the more expensive, and those can switch. Propane is less efficient for a gallon. It's more efficient typically in the way that it combusts, but a gallon of propane is 91,000 BTUs or thereabouts, and a gallon of oil, it could be as much as 135,000 BTUs. There's a lot more energy in a gallon of oil is what I'm telling you. And so if I'm buying gallon for gallon, I get more out of the oil, and as a result, even at kind of a level price, which I show here, the prices are similar. The oil is less expensive to heat with. It's dirtier though, for sure. Air source heat pumps can generally beat the oil and propane, and they're way better than electric resistance. Natural gas and geothermal kind of compete with each other, and on any given day, they're neck and neck, depending on the price of electricity and the price of natural gas. I would say right now, natural gas is less expensive than most geothermal systems, but only by a little. So if we want to electrify our heating systems, those are our 3 principal options: electric resistance, air source heat pump, and geothermal heat pump. And they're kind of on a continuum of solutions. And electric resistance, say for instance, for your hot water, could be a great choice. If you don't use a whole lot of hot water, it's not a whole lot of kilowatt hours, and it's a relatively compact, inexpensive, first cost, easy to replace. But if you want a better efficiency, you go to an air source heat pump water heater, and got a bigger family. Ground source also can help with water heating. It's a little less straightforward and a little more expensive to attach to, but there's ways that we do it pretty regularly. Here are some of the incentives. I'm not going to go into this in detail. I'm just going to give you kind of a broad brush about the incentives available. Geothermal heat pumps have both a federal and state incentives, or federal and utility incentives. There's a 26% unlimited tax credit for the rest of this year, and then it drops to 22 next year. It's the same as PV solar, and it's basically the same legislation, and those are for residences. National Grid also offers a $1,500 for every 10,000 BTUs of output. So it's about a ton. It turns out that for a home, that usually ends up being in the $4,500 to $6,000 kind of range in this area in terms of the rebate to a house. Central Hudson gives a little more generous rebate if you're down that way. Air source heat pump incentives, if you just do the mini split and it's just sort of that condenser outside and that one unit inside, it's about $500. It's $500 for every system. If you cover your whole house load with it, if you have air source heat pumps that heat your entire house, your incentive level is, again, per the amount of energy. And again, that's going to be in the 4,000 kind of range for a lot of homes. So it's a pretty significant rebate. There is no federal tax credit for air source heat pumps. Water heating, we've got air source heat pump water heaters get a pretty big rebate. So a unit that looks like this, you might get $700 off of that unit. If you use a desuperheater, which is a way that geothermal systems can assist in hot water, they give you a little bit, $100. If you have a dedicated geothermal system to make hot water, it's $900. But I have to say that's a lot more expensive to install as a standalone system. So that $900 doesn't go as far as you would like. If you do water heating and space heating and you electrify both, they give you a little bonus on your whole project too. And all of these things are accessible directly to the customer. There are some contractor incentives that are available too, but these are essentially flow-throughs to the customer. Very detailed slide, more for later. It's kind of a way to look at ground source and air source and compare the two, and just to look at a few different things. A lot of these things we've talked about tonight. A lot of people are curious about installation costs, and installation costs are an incredible range of it depends, unfortunately, which is always frustrating. So I give you some numbers just to satisfy you, to scratch that itch a little bit. But a 4-ton system, which would be kind of a standard, reasonably well insulated home, but say 2,500 to 3,000 square foot house, the geothermal system might cost, I don't know, 35,000 to 50,000, but then 22,000 to 33,000 after incentives. So one's a pre-incentive, one's post-incentive. Air source heat pumps are so varied. If you just do the part system where you only have one unit, that's going to be some thousands. Not unusual that it could be less than 6,000 if you just do one unit. But if you do your whole house, it could be 25,000 or more. It could be a very expensive system to try to cover your whole house. And I have my post incentives here. The incentives aren't as lavish, so you see the steps down are not as dramatic as the ground source, because the ground source has the federal tax credit and the utility rebate. I think that I'm going to conclude there. At the end of it, I have my contact information there. I also then included again Todd, so that if people get the slides, they can get us. But if you want to either read some questions or open it up to questions, I'm good.
Okay, perfect. So thank you very much. That was great. I learned a lot. One question was, when do those incentives that you talked about expire?
So the ground source heat pump federal incentives, 26% is for systems commissioned by the end of this year. So if you get your orders in soon, it's actually a little tough to get them installed by the end of the year in some areas and in some situations. 22% is in 2021, and then it sunsets. So right now, unless something changes, and I guess we hope it does, those expire. The National Grid, the utility rebates, we don't necessarily have a clear expiration date on those. I think that what they'll do is they'll update them periodically, but the direction that NYSERDA has handed it over to the utilities, and there's a sense that we really need to accelerate our heat pump adoption between now and 2050. So I don't anticipate those sunsetting. I don't know if they'll get better or worse. So the rebates, I think, will hang on for a very long time, I guess is my thought on that. And I'm pretty close to the whole situation. There isn't a clear expiration date.
Okay. Another question is, how do cooling costs for ground source heat pumps compare to traditional AC units?
So in air conditioning mode, yeah, since heating is the dominant thing, I tend to cover that more closely. So that's a heating slide, of course. Ground source heat pumps are about half the amount of electricity needed versus an air source equivalent. So if somebody's paying $400 or $500 in their total cost for air conditioning for the course of the season, they'd pay $250 if they had a ground source system. Air source heat pumps really are standard air conditioners. They benefit because they're generally higher levels of technology with this variable speed. On the hottest day of the year, though, they tend to have the efficiencies that are very similar to even single speed air conditioners. But again, they do benefit. I would say a new air source heat pump is probably about a 20 to 25% reduction in your air conditioning if you replaced an older unit. If you have a very modern unit that's dual speed or is already variable speed, the air source heat pump is the same as that.
So when you do the geothermal systems, you have the horizontal and the vertical. Are there significant differences in the efficiencies of those as well as the cost for installation?
Yeah, so the quick answer is the efficiencies really don't change too much. The way that I talk about it is that vertical systems tend to be the most predictable and reliable. If I couldn't do any math and I didn't know anything about the site, I would do a vertical, because when I go down to certain depths, there's a certain amount of consistency that comes with that. There's different rocks have different conductivities and things, but they're all within a range that's pretty easy to understand. Horizontal systems can be the equivalent of a vertical system as long as the ground conditions are suitable. So very coarse soils like sand, gravel, if it can't really hold water. So generally something that's really good for a leach field is really bad for a horizontal geothermal system, because I don't want that system to get completely dry. It'd be like sort of putting your heat exchanger in popcorn. I want it to be moist and have contact. So horizontals are a little more site sensitive. We do a lot of them, especially new construction. If someone's putting a shovel in the ground, they dig a foundation, we learn a lot about what the surface is like. And so we can tell if a horizontal will be a good way to go. You tend to do all of these systems. The first look that we give it is it possible to do? So if I could do a vertical or a horizontal or a pond, I'd probably do a pond. And the reason I do a pond is because it's the least cost installation, because I already have the pond. I don't have to dig as much, and they perform very, very well. Horizontal system and vertical system, I do it based on cost. If someone's excavation cost is zero because they own the excavator and it's their own time and it's just the cost of the fuel, I do a horizontal. If it's gravelly or I'm space constrained, I'm going to do a vertical. So we tend to look at the cost effectiveness of it, but I can really tune them all in so they work pretty much the same. I use more pipe when I do a horizontal than a vertical to make up for the fact that I'm not at a great depth. So we just account for it in the design.
Thanks. Jim has a question, so you can unmute.
Sure. Thanks, John, Todd, for the presentations. They were very good, and I learned a lot. One question I have for you, John, or actually two questions. First one is, how is this for this geothermal for something like a natural building structure, cob, I'm thinking, or say, earth ships? And the second one would be, second question is, how is it for non-detached single-family homes, such as apartment buildings, to retrofit to get to that 100% renewable and electricity and reduced greenhouse gas emissions?
Yeah, so anything we can do a heat load on, we can usually figure out a way to get the system in. So we just need to come up with our R and U values for whatever the material is, and infiltration values. You would need you would need mechanical ventilation in any new construction, no matter what material it is these days. So we can account for that. So all of these systems, both air source and ground source, will do a manual J heat load, which will then give us the information we need to be able to say, what size heat pump do I need? What size ground loop that feeds into my ground loop software as well, based on the ground conditions. So certainly, I'm trying to think, we have done all manner of things, but it's really just a question of doing the math on the R and U values of whatever the materials are. So I'd be happy to go through maybe a model with you sometime if you want. Renovating things it's a huge challenge for New York State, because a lot of New York State does not have central ductwork, and as a result, we have these baseboard water systems, radiator systems, steam radiators in some cases. The apartment buildings also often have either electric baseboard or baseboard water. So the first thing we think about when we think about converting buildings is, what's its distribution system now in terms of distributing thermal energy, heating and cooling? And do I want cooling? There's any number of buildings that don't have cooling, but they want cooling going forward, in which case we might be abandoning that system anyway. And if we need to put in a cooling system, usually there's air. Ductless systems are always a good thing to look at, and those can be done in ground source or air source. So that kind of ductless head right there, or other forms of it, can be installed in an apartment that maybe had hot water baseboard or even had steam radiators, and that can do the heating and the cooling. And then we just take that other system out or use it as an auxiliary system in the meantime. High efficiency baseboard can work. I just find that if I get into big plumbing and I'm getting into, okay, let's replace the insufficient baseboard system with a properly sized baseboard system, that's expensive too, in which case they tend to go to an air system, because then we can deliver heating and cooling and sometimes even ventilation. And so I see the ductless systems really playing a big role in the conversion of buildings. We do have some concerns, especially in larger buildings, where the amount of refrigerant line that you have to run in a complicated building is significant. And so an arrangement like this is variable refrigerant flow. There's metrics that we talk about pounds of refrigerant per ton of capacity. A ground source system that's packaged and everything is in one box and it's in the mechanical room is going to have a relatively small refrigerant charge, and then it's going to deliver through air or water to the building. These systems have a lot of refrigerant that's being pumped all around, and the global warming potential of refrigerant is high. So there's some hybrid systems that basically have a branch box that might be here, and then it's water delivery out to these. And so there's some ways to skin that cat to deliver with water more. But that's I think we'll probably go to more water delivery systems to fan coils, which are largely, just a version of what these different things are. There's console units, which looks like something you might put you see in a hotel room, or there's those heads, or there's the heads that are mounted up into the ceiling, and you'll just see this top part on it. It's probably not easy for people to see, but I don't know that I answered your question, but I took a couple of whacks at it at the piñata.
I'm just thinking, how about, what do you foresee for some place like New York City? We got huge apartment buildings, got projects, co-ops, things like that. Is this feasible?
It's only money. So yes, It's feasible. Is it reasonable to do? Do we have all of our technology done in an efficient way to do that? We don't. But I'll tell you what we do have. Right now, any building that currently is heated and air conditioned could be converted to a heat pump system. It could be, especially if it's air conditioned. Air conditioning, that means that somebody has designed a channel that we probably can link into somehow. The problems that we get in dense urban environments, Manhattan, or lots of places down in that direction, is that the balance of heating and cooling versus the available space is tough. So our sort of traditional, let's put in a ground loop next to a building, and that doesn't work on a skyscraper as well. Arrangements like this. So what we end up thinking a lot about, and there's a lot of, so Con Edison in their last rate case put in there that they're going to do district thermal studies for heat pump loops. So they're basically going to look at they have as you may know, they've got natural gas, of course, and then they have a steam utility in Manhattan as well. And they sell BTUs or pounds of steam. And those systems will ultimately need to be replaced. So we're looking at how could we put in a thermal infrastructure that would share energy amongst buildings in an efficient way, such that heat pumps in those buildings are centrally located heat pumps that would deliver cold or warm water to those buildings could work out. I saw I think it was Central Park. Someone did an aerial on Central Park. If we put geothermal boreholes all under Central Park, like everywhere we could, and then they had sort of this blob that was out about how many buildings it would serve. And it was pretty good. It was impressive, except for it was, 3% of Manhattan. If we put geothermal boreholes in every square inch, that we could. So we have to think about in those areas, how do we put in thermal networks that will work? And ultimately, the answer will be the Empire State Building every day of the year is running air conditioning someplace. If you have an internal conference room that's not on an external wall, it does not know it's 10 degrees outside. It's insulated from that. And if you put 25 people in it, it overheats. So what we need to do is we need to continually move towards having buildings that when that room overheats, that heat is used somewhere else in the building where it's needed rather than creating new heat. So that's the first thing, is lower the heat pump capacity that we need for buildings by having a sharing within the building. Then we look at networks of buildings and how they can share energy. And in a longer presentation that I do, they did this project. Burrow Huppold is an engineering firm, global engineering firm, and they did the London heat map. And what they did is they looked at where in London is heat created and where in London do they need heat. And they did a waste heat map some years later. And that informed, just as an example, the subway system gives off a lot of heat. Subway systems have the electric motors, they have people. They if you've ever been in a subway where the system isn't working well, you might be overheated. Where does that heat go? And you have to ventilate a lot because you can't have people way down in the ground without bringing fresh air down. So as you're expelling that hot air, they're using the hot air from the London subway system in a heat exchanger to create hot water for 600 homes as a demonstration. But that's the kind of thing we need to do. We need to think, where are we creating energy in a city while at the same time we're throwing energy away somewhere else? And how do we develop a network for those things? I was talking just before this started, and I think you were on for some of it, that NYSERDA is putting out a district thermal solicitation to address those types of things, coming up with creative ideas about how we can think about how to share energy within a building and then between buildings. Ultimately, in cities, unless we really use the water resources effectively or have water resources that we can use effectively, like rivers, like the ocean, we will still have a lot of energy we need to release into the air, just like we do now for air conditioning or chillers or things like that. But we'll need less of it if we network the buildings together, much less of it. What we're trying to get away from is evaporative cooling towers, so we don't have the dangers of Legionnaire's disease and things that we have with spraying water continually, plus all the water that's wasted in those processes. Anyway, it's perhaps an offline topic, but I think deeply about it, and I'm in conversations regularly about how to address big urban settings, because that's really, in New York State, I don't know, 65 or 70% of the problem is New York City and the boroughs, you know, from a greenhouse gas standpoint, which makes sense. A lot going on down there.
So here's a question. If I sit on top of the Marcellus Shale, would it be better to capture the gas?
Who is that? Who asked that question?
Anonymous with initials.
Most of the calls I'm on, they call that, they won't use the word natural gas. They call it fracked gas or fracked methane. That's the one that the environmentalists use. You know, gas, which is largely methane, is very effective at heating. That's for sure. The problem, the CLCPA is using the global warming potential is based on a time frame for different substances. So refrigerants are in the atmosphere for a certain amount of time, and there's a number associated with that. Methane is also, when it's released, is a very potent greenhouse gas. That's why we see flare stacks and things like on a landfill. We'll see them flaring, like you see that in Albany. And that's because the methane release itself is a more damaging greenhouse gas than the CO2 and water, largely, which is produced by combustion, by a big multiple. In fact, the multiple at a 20-year basis for methane released directly is about 86 or 90 times more potent than the equivalent amount of carbon dioxide. So that's a big difference. So, you know, fossil fuels right now, especially natural gas, which is a big topic, is so inexpensive as a fuel. I mean, it's amazing. It's like free energy practically. So anybody who has natural gas, you can complain about your bills. That's tough. Massachusetts, natural gas is about $1.30, $1.40 a therm. In Schenectady, New York, which I just looked at somebody's bill, it was 55 cents a therm last winter. That's 2 quarters for 100,000 BTUs, which is 100,000 lit matches. I mean, it's 100,000. It's like free. So it's certainly cost effective. You know, if you had a magical methane source to heat with that, I can't say it wouldn't be. But that just is not the direction the state is going, you know, kind of like it or not. I don't know that I answered that person's question. They could unmute and speak if they want.
Yeah, they can absolutely unmute. The follow-up was they're from Sullivan County and natural gas isn't available for them.
Yeah, I mean, one of the things that in geothermal drilling that we think about more and more as the technology gets more popular, we go to drill a geothermal well, and let's say it's 450 feet deep, or I need two 450-foot deep boreholes for a big house. If I hit natural gas, that's trouble. If I'm drilling thinking I'm not going to hit natural gas and I'm not set up for it. So there's parts of New York State that really are tricky because the natural gas is so close to the surface. Even in Ballston Spa or Ballston Lake area, you hit little gas pockets every once in a while too. Turns out that in Manhattan, in a lot of the boroughs, Westchester, you might go thousands of feet and not hit natural gas, but there's other parts of the state, obviously, where it's very, very tight to the surface and is a real, I guess, something we really need to get our arms around if we really go for geothermal big in some of those areas, because that's potentially a danger.
So with you touched on it briefly with the CLCPA, in terms of how that's going to really potentially push this forward. Do you foresee things like it becoming much more common for new construction to use geothermal? I'm assuming that it's much cheaper to start with geothermal than to go in later. Is it, do you think it's going to become more of a standard construction?
Well, we see, again, kind of a, like it or not, the way that it'll almost certainly will happen is at some point, with some fair amount of notice, the codes will change in a way that it would start a new construction where you're not allowed to put a combustion heating or hot water system in new construction. It's happened, it exists in many places in Europe actually already. And then the second is on replacement. So if I have an oil furnace, I can't put in an oil furnace, or I can't replace it even with a propane furnace. Brookline, Massachusetts changed their bylaws recently to say that starting, I think it was in 2021, that no combustion could be in new construction. They had lots of caveats and outs, and basically the Attorney General of Massachusetts said, not so fast. You know, there's laws that we're going to have to change before you can do those things. But there's a movement in a number of areas. But that's how it actually, if you look at the goals of the CLCPA and you look at the amount of conversions that we need to do for existing homes and any new construction, I think certainly by 2030, we can't extend natural gas. Certainly, that needs to really stop as soon as possible. So the expansion of natural gas needs to go away, and then we need to basically start to put in these codes where new construction wouldn't keep contributing to the deficit of in terms of the climate goals.
Mm-hmm. All right. Anybody else have any questions? No? Okay, well, thank you again, Todd and
All right.
John, for presenting this. So
Yep.
Thank you both very much.
All right, you know where to find me. Thanks for listening, everybody.
Thank you.
All right. Good
And
night.
thanks, Wendy and Todd.